In the next set of videos, we'll be looking into the topic of finite word length effects in IAR filters. Now, what happens in this primarily is because due to the coefficient quantization error. And if you look at this particular transfer function over here, h of z is equal to summation k equal to 0 to n b of k z raised to minus k by 1 plus summation k equal to 1 to m a raised to k z raised to minus k. So when you quantize the entire transfer function or the quantize the coefficients, the new transfer function will become h of z raised to h of z of q, which means the quantized transfer function will become, the coefficients are quantized out over here. So ak of q will be equal to ak plus delta ak, and bk of q will be equal to bk plus delta bk. So if we have a transfer function like h of z is equal to 1 by 1 minus 0.95 z raised to minus 1 plus 0.225 z raised to minus 2. If we have the coefficients out here 0.95, which will be equal to 0.1111, we truncate it to 3 bits, it becomes 0.111, so it becomes 0.875. The 0.225 coefficient, it is actually 0.0011. If we truncate to 2 bits, it becomes 0.001 equal to 0.125. So we can see that the coefficients change. Ultimately, when we change the coefficients, it could bring about a practical effect which would be affecting stability as well as the desired frequency, and that will be explained along in the problems 8.14, 15 and 16. So we look at the problem 8.14, and here as in this problem we have a second order IAR filter whose transfer function is given as depicted over here. It is 1 by 1 minus 0.05 z raised to minus 1 into 1 minus 0.45 z raised to minus 1. The question is study the effect of shift in pole location with a 3-bit coefficient representation in direct and cascade form. So we have the transfer function given here. Our first purpose will be to find out the roots of this original equation or identify the poles. So we actually manipulate this particular equation to make it into powers of 2. So we multiply it with z raised, or we take z raised to minus 1 common here, so it becomes z over here, and this becomes 0.5, while z raised to minus 1 comes out, and here it becomes z raised to minus 1 is taken out, and it becomes z minus 0.45, and this z raised to minus 1 into z raised to minus 1 creates z raised to minus 2, which is brought on top, so it becomes z raised to minus 2, sorry, z raised to 2 by z of minus 5, z minus 0.5 into z minus 0.45. So now from this we can understand the poles of the original transfer function. So that will be equal to 0.5 and 0.45. So these are the poles of the original equation. Now if we try to implement it in the direct form transfer function will be expanded, and this product will be expanded, and we get it as 1 by 1 minus 0.95 z raised to minus 1 plus 0.225 z raised to minus 2. So this is the equation for my direct form realization. So we quantize the coefficients, which is 0.95 and 0.225. This was explained earlier, so it becomes 0.875 and 0.125. So what we do here is we have h of z, which is a quantized transfer function, 1 by 1 minus 0.875 z inverse plus 0.125 z raised to minus 2. And what we do here is we create a transfer function. We have created the new transfer function, and we plot the output system. From that particular transfer functions equation, what we do is we take z raised to minus 2 common, so it becomes z square out here, and it becomes 0.87 minus 0.875 z plus 0.125, and when it is brought up, it becomes z square. The denominator becomes z square minus 0.875 z plus 0.125, and we find the roots of that equation out here. So when we find the roots of the equation, it is either 0.695 or 0.18. So we can see that now the poles of this equation are 0.625, 695 it should be, and 0.18. So if we compare this with the original pole, it was 0.5 and 0.45. So we can see that one of the pole is 0.5 and the other pole was 0.45. So there is a deviation from the original pole. This is what we make out of this particular problem. Our basic responsibility at this with respect to this topic will be to study the effect of the coefficient quantization, and what we have understood is that this particular thing will result in the change in poles which will be affecting the stability. So based on that particular thing, you have to comment on what is the change that happens. Our question contained two parts. One is to study the effect in direct form and cascade form. So direct form is over. So when we realize it in the cascade form, we already have the system out over here. It is in the product form, so it is already in the cascade version. So what happens here is again the poles are same, and when we change the coefficient, it becomes 0.5. When it is converted to binary, it is in this form. When we truncate it to 3 bits, it still remains in that form. But 0.45, it remains, there is a change, it becomes 0.375. All you need to do is study the change happening here, and you can see that it has changed. So h1 of z new remains the same, h2 of z is changed. So what we do here is we realize the structure and we try to examine the poles of this particular equation. So in this particular thing, we can see that one of the pole is 0.5 and the other pole is 0.375, which has changed from the original pole. Original pole was 0.45. In comparison, it has become 0.375. So we studied the fact that one of the pole remains same and the other pole is close to the original pole. So I hope this clears the topic.